in order to enhance your learning as we learn to read electrical diagrams, I would suggest that you print out the diagram and then color code how you think it works first, then watch the video. Keep in mind red is power all the time. When red is switched on, it becomes orange, and green is ground at all times. And when we switch that green on, it becomes yellow. Now you're going to discover a whole lot more by trying to color code it yourself first, because you'll have questions. And then hopefully as we watch the video, we'll answer those questions for you. And remember, you can download the diagrams from our website. Just look for the specific video and the web page, and the diagram should be there. Now there's more to this diagram than you first see when you first glance at it. There's actually quite a bit here. So let's take a closer look. Now here's a tip. Power usually comes from the very top of the page. If you notice up here it says battery, and as we draw that in, it travels downward. It travels downward until it gets an open. At the front blower motor relay, you'll see that switch is open, so it stops, and then it goes down through the electromagnet, and it stops because there's no ground there. Now remember, it always stops at an open. And ground usually starts at the bottom of the page and travels upward. This is how they're usually drawn, and again, it will stop at an open. Now be sure to notice this because it's very important. Dotted line boxes. We have two of them in this diagram, and dotted line boxes means it's a control device, but there are more pins that are shown. For example, this is a diagram for the front blower motor, but the HVAC control could also control the rear blower motor, but the only thing this diagram is showing is the front blower motor. So these dotted line boxes means there's more in this integrated power module, and there's more to the AC heater control than is listed in this diagram. The other side of that is the solid line boxes, and we have two of those. The one is the front blower motor relay, and the other one is the blower motor resistor. Those are solid lines. That means that they are complete. They're control devices, but all the pins are there. You don't have to wonder if there's something more. Now these are resistors. Resistors resist, and they use up some of the power, and they change the amount of current that's going to flow. Of course, current flowing in a motor means how fast can it flow. One more thing to notice here. We've got a fuse. Now this fuse, notice, is internal in integrated power module, so it may or may not be serviceable, but this is where it's located. So let's see how this circuit works. First off, what's the purpose of this diagram? To make the blower motor run. So if that's the problem you're having and that's what you're trying to resolve, this is the diagram you need. Now we always want to locate our major components first. For our blower motor, we got our power coming from the top, a fuse, a front blower motor relay, an integrated power module, blower motor resistor, HVAC control, and an AC heater control. That's our main components. Now, here's something to remember about all diagrams. Diagrams are always drawn at rest. Now that means the key is off, nothing's working, and all the switches are in their unactivated position. This is a rule we go by. The only exception to that is that sometimes in a sub-diagram it may be noted that it is in the on position, but it will be specifically noted for that. So if you don't see it specifically noted, just remember they are drawn at rest. So this one is drawn at rest. Battery is hot wired connected through the blower motor relay, and you can see it stops at an open. Now the ground is the same way. It starts at the bottom of the page and travels upward, and it stops at an open. So this is at rest. Always draw your diagrams first, complete at rest. In other words, the power to all the opens and the grounds to the opens. So this is where you would test everything. Now let's turn the front blower motor to the on position and the front blower speed to the high position. You'll see number 5 in the heater control is listed right here. So that's where we're going to rotate our switch to connect to number 5. Now I want you to notice that the HVAC control is a dotted line box inside the other dotted line box. So this is all circuitry connected. That's what that basically means. It's a control device. Now this means is that the control switch It's also a rotating mechanical dial. So as we turn with our hands the mechanical dial to select our speed, it also has circuitry in there to complete the circuits that are necessary. Now notice this is controlling for the ground side. So the relay control and the blower speed, they all begin at the same time. Now this front blower HVAC control then has ground to it. When we turn the switch, rotate the switch, it is then going to, through its circuitry, give ground to the front control module. Notice that that front control module has power through the electromagnet, but it's sitting there looking for a ground. Where does it get its ground? It gets it from the HVAC control. So when we turn this on, now that was pretty fast, but if you look at it, our HVAC control was rotated and turned on, so it sent ground to the front control module, which activated the electromagnet, which when it activated, it closed the switch on the front blower motor relay. So we changed from red to orange, and it travels down through the fuse, directly through the blower motor resistor, and sets there at the front blower motor. And the front blower motor, again, remember we were looking for position number 5. 5, when we rotated our switch, connected directly to ground, so it changes from green to yellow, and that gives us a direct ground path to the motor, so the motor runs. Now note that position 5 is unresisted. There's no resistors in there, so it's going to have its maximum power and ground, and that motor is going to run at high speed. Now, let's say that we switch to position number 2, more of a lower speed. Now notice that position number 2 is resisted. So when we make this connection, it works the same way. But look at position number 2 now. Position number 2 is directly connected to green ground, so it turns yellow, and it travels down. On its way to the motor, it has to go through 3 resistors. So obviously this motor, being resisted, is going to run much slower. But notice that we've got connections at 1, 3, 4, and 5 as well. Now you may be asking, why is that? Well, before on position 5, it was connected directly to ground, and now it's number 2 that are connected directly to ground. But 1, 2, 3, 4, and 5 are all directly connected to each other as far as continuity goes. The wires are physically touching, and there's no opens in them. So when we switch to any position, for example here in position number 2, we're going to change that from a switched ground, from the ground to a switched ground, and it's going to turn yellow, and all of those wires that are connected are going to turn yellow or have ground at them. So if you were testing this switch, you would have ground at all of those pins. Now number 2 is the only one that has a direct path to the motor, but it has 3 resistors in it. So when you're in this position, the motor is going to run with 3 resistors in it. Now if you had a complaint, and that was that speed 4 and 5 worked, but no other speeds were working, where would the fault be? As you look at this, if each speed were to work, if they were to work like they should have a completed circuit. In other words, each speed as we rotated that dial should have a direct path from the ground to the motor. But if we had one of these resistors that was blown out or burned out, then in this case, if this resistor was burned out, 4 and 5 would be complete circuits, but 1, 2, and 3 would be incomplete because of the burned out resistor. That's where our open would be. Now, let's say that you wanted to prove this, and you didn't know if it was the switch or the blower resistor, but you knew your blower motor only ran on the 2 high speeds. How would you prove that it's the resistor and not the switch? Or on the other hand, how would you prove that it's the switch and not the resistor? What evidence would you go looking for? Now we've got a solid box down here at the resistor, so everything's available at the resistor. If the switch is good, you should have ground at each point as you rotate the switch. So if you put a power probe at position number 1, you see 1 is directly connected to ground. Now it is physically connected to 2 and physically connected to 3, but it is not connected to 4 and 5 because of the blown out resistor. So you would only have ground at pins 1, 2, and 3. At connector positions 1, 2, and 3. Now if you moved your power probe to the speed position for number 2, you'd have ground at 1, 2, and 3, but not 4 and 5 for the same reason. You've got a blown out resistor. Now move your power probe to number 3, you've got the same scenario. 3 is directly connected to ground, so 1 and 2 will be, and 4 and 5 are not because of the open in the circuit. Now you move your power probe to number 4. Now number 4 has a direct connection to ground, but 1, 2, and 3 do not because of the broken circuit, the blown out resistor. 5 does, but 5 isn't open. 4 is the only direct path to ground, but you're going through one resistor, so this motor is going to run a little bit slower in 4 than in 5. And when you move your power probe to 5, 5 is the direct path unresisted to the motor, so it's going to blow it high, but you still would have a ground at 4. So understanding how this diagram works, you can actually prove and get your evidence here that the switch is good and the blower motor is where the problem lies.